Thank you for the introduction. At first, I would like to thank organizers for giving me the opportunity to speak today. I will tell you about our recently developed web service for GPCR virtual screening based on three-component decision support system. I will start with a short introduction to GPCR research. It is needed to fully understand the level of difficulty in GPCR virtual screening and possible achievements at the current stage of GPCR drug discovery. I believe that much has been already told in last days about machine learning, AI, and all the related issues, so I will not focus here on this part. Instead, I will tell you what exactly can be retrieved from public GPCR data that is currently available to the whole research community. But before this, let me remind you about the significant progress that has been made to GPCR structure determination in past 10 years. What we see here is a phylogenetic tree of GPCR protein family, characterized in 2008 by Lagerstrom et al. GPCR tree consists of a few major branches. Today I will focus on two classes, A and B, corresponding to rhodopsin-like and secretin-like GPCRs. In 2013, only a few GPCR structures were determined, while in 2023, most of GPCR tree was already covered with structures of active and inactive state receptors, as you see here. It all started with the first structure of GPCR receptor solved with X-ray crystallography in year 2000 by Palczewski and colleagues. Although it was known before that GPCRs consist of 7 transmembrane helices, it was the first structure of a GPCR receptor solved in atomic details. Why atomic details are so important? Low resolution, coarse-grained structures of proteins hardly can provide correct orientation of ligands in binding pockets. Without precise determination of ligand binding mode, it is hard to modify its structure to improve its potency as a drug. Atomic details are also important for virtual screening because even a single amino acid in the binding site that is mispredicted in terms of side chain rotamer conformation affects results of screening. This is because GPCR ligand can be highly selective for a certain receptor subtype. Design of highly selective drugs is needed to, for example, exert analgesic effects through opioid receptor signaling without causing adverse events such as opioid addiction or opioid overdose. In 2003, another structure of rhodopsin in atomic details was solved. This time, it showed that rhodopsin can associate in functional dimers. However, not earlier than in 2007, a second structure of GPCR has been solved. It was beta-2 adrenergic receptor, solved by Kobilka's lab. Successful approach that was applied here involved camelid monoclonal antibodies for intracellular loop 3 that allowed to obtain diffraction quality crystals. Also, protein engineering, such as, for example, thermostabilizing mutations introduced by Heptares, turned out to be successful in X-ray crystallography of GPCRs. Finally, to obtain active state receptor structures in 2008 and 2011, nanobodies had to be included for the receptor stabilization. Without this, only quasi or somehow intermediate state receptor structures could be obtained. Just before the grand opening of cryo-EM for GPCR structure determination, two GPCR competitions have been organized. The aim of GPCR Doc is to predict GPCR structures, similar to CASP competitions, but additionally ligands binding modes have to be also predicted. In GPCR Doc 2010, first peptide-bound GPCR structure has been released, while in GPCR Doc 2013, first non-class A GPCR smoothened receptor has been released. In 2017, first high-resolution structures of GPCRs have been determined with cryo-EM, and since that year, a rapid progress in GPCR structure determination has been steadily observed. I participated in both GPCR Doc competitions. We did quite well in GPCR Doc 2010, and we won in GPCR Doc 2013 in prediction of the 5-HTB serotonin receptor. We also did quite well in a case of a more difficult task of distance homology modeling of smoothened receptor, but we were not mentioned at all. And despite our success, we are delighted by reviewers almost 3 years to publish a paper describing our results and methodology used in GPCR Doc 2013. How did we win? At first, I improved sequence alignments used for model building by including sequence profiles. I also used multiple template modeling to release the model from a single template's restraints. This was particularly useful for distance homology modeling. But like many others, I used Modeler and Rosetta for loop modeling. If you check our results from GPCR Doc 2013, you'll notice that some of our models are not that perfect as they could be. This is because we treated receptor models just as tools for predicting correct ligand binding modes, and protein structure was not the main aim here. Our method could be described as ligand-based selection of protein models. We used ROC curves for quality assessment of receptor models. Our method has been implemented as a web service, GPCRM. Do we have sufficient compounds to assess GPCR model quality? Unfortunately, many compounds are the property of pharmaceutical companies and are not released to public for obvious reasons. And many orphan GPCRs do not have any known ligands so far. But what do we have? For example, in a public Campbell database, sometimes compounds in Campbell retrieved datasets are too similar, like shown here. In such case, hardly any new compound could be found. Diversification of chemical scaffolds is something what we really would like to have in our training data sets. Another problem is coverage of possible ligands efficiencies. Frequently, we have only very good and very bad compounds in data sets, such as shown here. Such data sets could be used for binary classification, active versus inactive compound, but hardly could be used for precise prediction of the compound efficacy. Do we need much data for training? Obviously, yes, especially to train neural networks, but hardly ever it could be true, like here, like shown here. Although we have some large training datasets in GPCRVS, There are also many highly limited datasets that are hardly sufficient to use for training. Finally, not all ligand activity metrics are standardized. Word active in Campbell can have many meanings. Sometimes only a small part of large Campbell datasets can be used in training. Sometimes a correct assignment of exerted effect on the receptor is missing, and we cannot tell if a ligand is a modulator or classic agonist. As you see, GPCR drug discovery constantly represents a high level of challenge. We have recently built a three-component decision system to support selection of GPCR drug candidates. GPCR ligand data is used for training of machine learning algorithms. Each model is trained on one receptor dataset, including its active compounds. Active does not mean here that ligands are only agonists. They can be also inhibitors. GPCR structures and models are used in molecular docking to estimate ligand binding affinity and its possible binding modes. Finally, results of all three components are taken together to provide activity profiles that are unique to each tested compound. Currently, there are two classes included in GPCRVS, class A and B. Receptors from both of these classes are endogenously activated by peptide agonists. This is why there are many active compounds in Campbell datasets for these receptors. Usually, peptide compounds are represented by a sequence of amino acids, while small molecule compounds are represented, for example, by SMILES descriptor. These are two representations, rather cannot be uniformly used in training. We found a solution to combine these peptide and small molecule compounds into one dataset. This is done by peptide truncation to 6 residue fragments. This truncation is usually done at the C-terminal site, as most known peptide ligands of GPCRs interact with receptors with their N-terminus. One of our approaches implemented in GPCRVS is ligand-guided selection of structural GPCR models used for molecular docking. Protein structures can act as classifiers and can differentiate between active and inactive compounds in molecular docking. Here we used Brian-Schoichat directory of useful decoys to generate inactive compounds for our ligand datasets. Based on ROC curves generated in molecular docking, we selected the best performing receptor structures. This method can be used not only for selection of the best homology models, but also to select PDB structures that are the most suitable for virtual screening, as we shown in 2021. This method can be also used in selection of the best protein conformations from the ensemble of conformations generated with molecular dynamic simulations or obtained with NMR, as we shown in 2019. How many receptors are currently included in GPCRVS? It seems that it is not a large number, but as you see here, almost every protein structure obtained from PDB, GPCRM, or even AlphaFold or beta had to be refined in terms of loops or N and C terminus. Sometimes loops were missing in PDB structures, as receptors demonstrated high conformational variability in these regions. These refinements are shown here in red. These two groups of receptors from class A and B bind peptide and or small protein compounds and represent one of the most difficult targets for virtual screening. Once some people even considered class B receptors as undruggable targets for small molecule compounds, which is rather not true as it was observed later. In the second part of my talk, I will show you examples of tests performed for GPCRVS. These results has been just done during the recent update. At first, we used classic tests of performance using 10% of randomly generated compounds from Campbell datasets that were not used in training. Here on these plots, I show you the difference between experimental p-Campbell values and predicted p-Campbell values, which should be 0 or close to 0. p-Campbell is a descriptor used in Campbell for describing ligand activity. p-Campbell is usually set to standard values between 0 and 10 or 11. 0 means here an inactive compound. As you see here, the activity of most compounds was correctly predicted. The same satisfying results were obtained for class A receptors with a few exceptions. These exceptions refer to receptors for which there were no sufficient data in Campbell for training of ML models. Also, chemokine CXC receptors demonstrated moderate challenge in activity prediction due to a distinct distribution of ligands in training datasets, as I've shown you before. Similar results were obtained with deep neural networks implemented in TensorFlow. Same, some chemokine receptor performed slightly worse. Another test we did involved patent compounds from Google Patents. These compounds were not included in Campbell at the time of testing, and they were also not included in our training datasets, and rather not included in datasets used by Swiss Target Prediction Server. Unfortunately, no allosteric or orthosteric assignment were available for these compounds, but most probably they are orthosteric ligands. As you see, a satisfying level of the prediction quality, outperforming Swiss target prediction, was obtained with 2 out of 3 components of GPCRVS. In most cases, it was light GBM together with TensorFlow component. However, Autodoc Vina also performed quite well in drug target class prediction. Unfortunately, we rarely observed agreement between all 3 components of GPCRVS, but still it is in accordance with the complementary of ligand-based and structure-based approaches to virtual screening. What about functionality tests? In what tasks?
We're going to have to wrap up. That's already 20 minutes. Have you?
Yeah.
Sorry.
I have 30 seconds.
Right.
What about functionality tests? As you see here, it can be used to discard inactive compounds that are not GPCR ligands at all. It can also discard so-called paints compounds, such as aspirin or catechol, that demonstrate falsely positive results in virtual screening. GPCRVS can also show the binding site of class B receptors are indeed fitted to peptide-like compounds. Though not always, but in many cases GPCRVS correctly predict a certain subtype of a receptor for a tested compound. Although both class A and class B receptors implemented in GPCRVS are peptide-binding GPCRs, it can accurately predict to which drug target class a tested compound by professionally. What about failed prediction? They are mostly due to certain overlap between ligand datasets for each receptor in Campbell. In addition to activity and binding affinity prediction, we can find structural fragments or scaffold fragments that are the most crucial to the ligand activity. Finally, GPCRVS can distinguish between active GPCR-like compounds and inactive compounds. As you see here, to accurately predict if a compound is GPCR-like or not, machine learning should be used rather than molecular docking. And I would like to mention people who contributed to the development of the current version of GPCRVS. Paulina created a peptide dataset and did structure predictional modeling. Przemek, IT manager, took care of our cloud resources and core facilities. This study is mostly supported by Faculty of Chemistry, University of Warsaw, but at the beginning in 2020, we received a small grant from National Science Center. Thank you.